Assalamu alaikum. Hello everyone. We move to our next lecture, functions and truth tables. Truth tables are tables with all states of the variables and the values of the functions for each state. A Boolean function is described by an algebraic expression consisting of binary variables, the constant 0 and 1, and the logic operation symbols. For example, might have a function such as f equals a and b or not c d, or this is function 1, function 2, not x, not y or z. Usually, we write the function and the list of variables. For example, function 1, because we have 4 variables, a, b, c, d, equals a, b, or not c, d. In this way, by means of Boolean algebra, we express the function. Another way to express the function is the truth table. For example, if we have the function f of xy equals x not y or xy, for example, we list all states of the variables. Since we have 2 variables, then we have 4 states. The number of states in the truth table equals 2 to the power n, where n is the number of variables. Here the function x not y, here 1, xy here 1, and in the remaining values are zeros. So we can express Boolean functions in different ways. In algebraic forms, by means of truth tables, or logic circuit. All the forms are equivalent. We can derive any form from the another. By means of logic circuit, for example, if we have the circuit A, B, A, C, etc. Exclusive of function f. The function f is now given by means of logic circuit. From this logic circuit, we can derive both the algebraic form and the truth table. Next, how to derive a function from the truth table and vice versa. Suppose we have the following function of 3 variables. Function f of a, b, c. How can we derive the value of the function or express the function in an algebraic form? Do you see the function is 0 here, where a is 0, b is 0, c is 0, or a in complement form, b complement form, c in complement form. Function is 1 here, where a in complement form, b in complement form, and c in normal form. So we can write here, it is 1 when not A, not B, and C. The next state, so here we have or 1 when not A, B, not C. Or in this state, A, not B, not C. A, not B, not C. Or in this state, A, not B, C, or in this case, A, B, C. So in this way, we derive the function in algebraic form from the truth table. Next, we are going to answer the question, how many functions can we generate using n variables? In general, if we have n variables, then we have 2 to the power n states. For these states, 2 to the power n states, we can generate 2 to the power n, 2 to the power number of states, functions. Using n variables, we can generate 2 to the power 2 to the power n different functions. For example, if we have 2 variables, if n equal 2, then the number of functions equals to 2 to the power 2, 4, 2 to the power 4, 16. If n equal 3, we have 2 to the power 3, 8, 2 to the power 8, then we have 2, 5, 6 different functions. If n equal 4, then we have 2 to the power 4, 16. 2 to the power 16 functions. Different functions. This is more than 65,000 and something. Because 2 to the power 10 is equal to, I can write it, 2 to the power 10 multiplied by 2 to the power 6. This is 64, and this is, so you cannot list these functions even for 4 variables. However, we are going to list all the functions for 2 variables, and in the same manner you can continue for more variables, not by listing them, by knowing the logic how they are generated. The functions for 2 variables are 16 functions. We name them from F0 to F15, and they are, here are the states of the variables: 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 3, and 4, 0, 1, 0, 0, 5, 0, 1, 0, 1, 1, 1, 0, and 15, 1, 1, 1. These are the 16 functions that we can generate using 2 variables. The first note, F0 equal constant 0, because it does not depend on the state of x and y. It is 0 in all the states. So if 0 equals 0. If 15 equals 1, constant 1, because it is 1 in all states and does not depend on the values of x and y. You can note that if 0 equals the complement of 15 and if 1 equals the complement of 14, if 2 the complement of f13, etc. etc. And if 7 is the complement of f8. Now we move to f1 and other functions. F1, as we learned, equals 1 here. So we can obtain the algebraic form for f1 from the truth table. It is 1 when x equals 1 and y equals 1. Only here. So x and y. X and y. And it is the AND operation we already know. If 14, yeah, equals the complement of 1. So it is equal to x and y or not. And it is this, not x or not y. If 14 is the NAND, if 1 and if 14 is NAND. Really, you can obtain a 14 if you are not convinced. If 14 you can write equals to 1 when not x not y, or 1 when not xy, or 1 when x not y, equals here not x not y or not xy is equals to not x, or and again not x not y, x not y together, they differs only on x, so we can write not y. This is a 14, which is really here, or according to De Morgan's theorem, it's equals to x and y, we complement y's or not, So this is about f1 and f14. f1 and constant 0, constant 1, NAND. Next we move to f2. f2 equals 1 here when x not y, x not y, x and not y. 0 and here x not y. Now if 13, we can derive it from here, equals complement 2 equals x and not y or not, which is equals to not x or y, not x or y, 13. Or you can derive it 13 equals from the truth table, it is 1 here, not x, not y, or 1 on not x, y, or here on xy, which is equals to these two terms differs only on not y, so we can remove it and write not x, or, and this differs on not x, so we can write it y, and this is the same as here. Next, 3. The function f3 equals to, really you can see it is equals to x directly, but even if you write x not y or xy, it is equals to x. So 3 is equals to x. And if 12, you can see it directly, and no need, it is not x, not x. Since f12 is the complement of 3, is not x, or directly from the table. Next, 4 equals 1 only here, when not x and y, not x and y. Yeah. So if 11 equals to not x and y or not, which is equals to x or not y, x or not y, if 11. Again, x or not y. Again, I'll do it, derive it from the truth table as an additional exercise. If 11 equals not x, not y, or 1 also on x, not y, or on xy. These two terms differs in y, in x, so not y, or, and this differs on x, on y, so we write x, and it is the same as here. Next, 5. Five equals to here 1 on not xy, or, and here one on x and y. And you can see that is equals to 1, and it x or not x equals to 1. And relief 5, if you look at it, 0, 1, 0, 1. It's y, 0, 1, 0, 1. If 10, 1, 0, 1, 0. So directly you can write it, not y, not y. If 6, equals to here, 1 here on not x, y, or here on x, not y. We cannot simplify this expression anymore, and you know this function, it is x exclusive or y. And you remember maybe the gate for exclusive or y. So if 6 is exclusive or x exclusive or y. Nine equals to not x, not y, or xy. And you cannot simplify this function, and it is exclusive norm. Exclusive norm. xy, x exclusive norm, y, or equivalence, or, because it is 1 when the two variables are the same. This is it 9. If they are 0, 0, it is 1, and if they are 1, 1, it is 1. It is the complement of F6. F6 and F9 are complementary. Next, we have 7 equals to 0 here, not x, y, or x, not y, or xy, which is equal to, we can group the first with the last, which give y, or, and we can group the second with the last, x. Do you see, we can, any term can participate more than once in a grouping, since A or A or A equals to A. But we have to take any term at least once. So, you know this, it is OR, the OR operation, and this is the gate for OR, as you remember. So F7 is X or Y. F8 is the norm, the complement of F7 and equal X or Y or not. And this is the norm XY, and here we have X or Y or not, and it's the no operation. f8, the complement of f7, x or y or not. Or you could really f8, write it f8 from the truth table, it's one only here, on not x and not y. And according to De Morgan's theorem, it is x or y or not. It's the norm. These are the 16 functions that we can generate using two variables. For this day, thank you.